So the first example, say our objective is to generate a uniform flow. Uniform flow. So you have to keep in mind that what is our objective? Our objective is to generate mathematically some physical flows by finding out the proper expressions of the capital F function. So one flows, all these flows are inviscid and irrotational type of flows. Let us say one is uniform flow. So uniform flow may be in different directions. Let us say that this is x and this is y, and you have a uniform flow which is having a velocity v making an angle theta with the x axis, or say alpha with the x axis. So you have such uniform flow, a free stream flow inclined at an angle alpha with the x, that is the flow we want to generate. So what is u here? U is v cos alpha. What is v? That is small v, v sin alpha. So u minus iv is what? V cos alpha minus I sin alpha, right. So v e to the power minus I alpha, and this we want as df dz. So f is v e to the power minus I alpha z, maybe plus something, plus some p plus iq you may put. It is not always necessary to put that, but we will see that if we want to generate a body of a particular shape, then this constant will be useful. But just for a free stream flow you need not use this, because then you need not generate a body of a particular shape. So this is not necessary. So you may choose a reference such that, so you have to keep in mind that this f is like f is called as a complex potential. So the name of f is a complex potential. So it contains both the stream function and the velocity potential, and you see those are not fundamental quantities, those are just mathematical quantities. Fundamental quantities are the velocities, for which gradients of those parameters are important, absolute values are not. That is why if you add some extra constant, it does not matter. When you calculate the gradient or the derivative, this does not matter at all. So this is just a choice of reference. Depending on your choice of reference, you may put this as 0 also, it makes no difference, it gives still the same velocity field. Now if you using this example, let us say that you want to generate a uniform flow along x. If you want to generate a uniform flow along x with a velocity, say capital V equal to u infinity and alpha equal to 0. So what is f in that case? U infinity into z, right. Now this is phi plus I psi, right, z is x plus iy. So what is phi? Phi is u infinity x, psi is u infinity y. So how do the streamlines look like? Constant psi lines, lines with y equal to constant, right, parallel to x axis. So these are the streamlines, these are psi equal to constant. Lines of phi equal to constant, x equal to constant, that is lines parallel to y axis. So these are phi equal to constant, and you can clearly see they form a net of orthogonal lines. Okay, this is a very simple example, but this demonstrates the use of the method. From this we will go to more and more complex examples. The next example that we will talk about is something called as a source. What is a source? Source is something like this. Let us say that you have a point, this point is radially emitting some flow in the radial direction. So this is a point through which you have flow emerging radially from all directions. Just imagine like that, so that the velocity component Vr is inversely proportional to the radial location. That means at r equal to 0, this point, if it is r equal to 0, then Vr theoretically tends to infinity, and therefore r equal to 0 is like a singularity point that we have to understand. Now let us say that Vr is equal to c by r and V theta equal to 0. So this is a pure radial flow. Okay. Now how is the source defined or designated? It is defined or designated by the rate of flow from the source. So how do you find out the rate of flow from the source? If you consider an imaginary circle located at a radius r from the center, then what is the rate of flow? This is a planar thing. So the rate of flow, when you consider, you have a circle like this, you have flow perpendicular to the face of the circle, it is a planar thing. So when you consider that area, the area just becomes sort of the perimeter over which the fluid is flowing for a planar 2 dimensional case. So say you consider unit length or a length of L, it becomes 2 pi r into L. Here it is a planar case, so just 2 pi r. So the flow, let us say small q, is Vr into 2 pi r. So that is c by r into 2 pi r, that means c is q by 2 pi. This q is called as strength of the source. Why it is the strength of the source? It physically indicates the rate of flow from the source. So if q is larger and larger, you have the higher and higher rate of flow emitted by the source. So this is called as the strength of the flow. So what is the velocity field here? Let us just write the velocity field. You have Vr is equal to q by 2 pi r, right, V theta equal to 0. Remember df dz is Vr minus I V theta into e to the power minus I theta, right. So this is q by 2 pi r e to the power I theta, right. Now remember that r into e to the power I theta is just another way of representing the complex number z, right, in the polar form. So z is r e to the power I theta. So this is q by 2 pi z. So you look into this thing that although df dz exists, it is an analytic function, but that has a singularity at z equal to 0, right. So at z equal to 0, it ceases to be complex differentiable or analytic because of this division by 0. So these such points are known as points of singularity. Now what is the form of f? That you can find out straight away as if by integrating these. See, once you write it as a function of z or a single variable, it is as good as the simple differentiation. So f becomes q by 2 pi ln z. Right. So this is the form of the potential complex potential function f, and you can write it in terms of the phi and psi. So you can write, for example, f as q by 2 pi ln r e to the power I theta, right. So that is q by 2 pi ln r plus iq by 2 pi theta, right. So it is just like phi plus I psi by definition of f. So what are the phi equal to constant lines? Phi equal to constant lines are r equal to constant lines, that is the radial lines, and psi equal to constant lines are the theta equal to constant lines. So what are theta equal to constant lines? So if you consider a net like this, just different lines like this. So what do these straight lines indicate? These are what? These are theta equal to constant, right? So theta equal to constant are basically the radially diverging lines, and phi equal to constant are r equal to constant are these lines. So r equal to constant lines are what? R equal to constant lines are the equipotential lines. So these are phi equal to constant lines, and theta equal to constant lines are psi equal to constant lines. So you can see that physically it represents a sort of, that is a source at the origin, and there may be flow like this. Okay. So you can see that the shape of streamlines gives you an intuitive idea of the nature of the flow. If the flow is in the opposite direction, that means instead of radially diverging, it is converging to the point, the origin, then we call it a sink, just in place of a source. So if Q is positive, we call it a source. Till now we have implicitly presumed that Q is positive, but if Q is negative, we call it a sink. Now we have seen that what are the shapes of the streamlines and the equipotential lines for the source and the sink. Let us now consider a superposition of the source and the sink. Say we consider now an example like this, that let us say that this is the real axis, that is the x axis, then you have a point epsilon comma 0, and you have a point minus epsilon comma 0. At the point epsilon comma 0, you have a sink of strength Q, and at the point minus epsilon comma 0, you have a source of strength Q. Okay. Our objective is to find out the velocity field and the stream function, velocity potential, all these things. Okay. So we can see that whatever we have learned till now, it is a combination of that effect, but the question is it a linear combination or not? To understand that, keep in mind that both the stream function and the velocity potential satisfy the Laplace equation. So you have Laplacian of phi equal to 0, Laplacian of psi equal to 0, that means Laplacian of phi plus I psi also equal to 0, right, that means Laplacian of f equal to 0. This is a linear differential equation. That is why if f equal to f1 is a solution and f equal to f2 is a solution, then f1 plus f2 is also a solution, right. That means you can consider this problem as a linear superposition of the effect of the source at a point and a sink at a point. So you can just add those together, that is the advantage of the linearity of the problem. So let us try to do that. So we will now try to write f. So now you tell what should be the f, what should be the contribution of f, say f1 for the source of strength Q. So Q by 2 pi ln of what? See, now it is a shift of origin. Earlier we considered the source or sink at the origin, now it is located at a different point. No, we will write it in terms of the z. So remember that f is q by 2 pi ln z. So we will write z, we will make a transformation or a translation of z to something, z plus something or z minus something. What is that plus or minus? Yes, z plus epsilon, right. So it as if you have used a new coordinate system capital Z with its origin located at the source, right. Then for the sink minus q by 2 pi ln of z minus epsilon, now it is located at epsilon. Let us consider that epsilon is small, but how small or how large we will see, that is what we need to consider. Before that we will just do a bit of a manipulation on this. The whole objective of this manipulation is we will write the terms in the form of ln of 1 plus something, so that we can use the logarithmic series expansion. Okay. So q by 2 pi right. So let us just try to expand this. Log 1 plus this one, we assume that epsilon by z is small. So log 1 plus x, what is the expansion? X minus x square by 2 and so on. I mean we need not write all the terms, minus q by 2 pi, then this is minus epsilon by z, then minus square terms remains the same and so on, right. In the limit as epsilon by z is small, then like you may write it approximately as q by 2 pi into 2 epsilon by z, right, in the limit as epsilon by z is small. So you have q epsilon by pi z. So this we just write in a shorthand notation as some m by z, where m is q epsilon by pi. Such a case when epsilon is tending to 0, this is known as a doublet. So that is the name of this one, when you have this as epsilon by d, epsilon by z or epsilon tends to 0. But important thing is, although epsilon tends to 0, we have assumed that q epsilon by pi is finite, but q epsilon by pi is finite, that is very important, because you have to understand that if epsilon tends to 0, you always have a chance of q epsilon by pi also tending to 0, but maybe q is so large, so it is a product of two quantities that is important. Q is very large, epsilon is very small, but q into epsilon is finite, that is what we are thinking about, and this is known as a doublet, that is the name. So let us try to make a sketch of, or try to identify that what should be the corresponding natures of the streamlines and the equipotential lines for a doublet. So what is f? F is m by z, that is m by or m r e to the power m by r, sorry m by r e to the power minus I theta, right, that is m by r cos theta minus I sin theta. This is phi plus I psi, right. So let us try to identify what are psi equal to constant lines. So what is the expression for psi then? Minus m sin theta by r, right. We may easily convert it into Cartesian coordinates by multiplying both numerator and denominator by r. R sin theta will become y and r square will become x square plus y square, right. So if you want to identify what are the streamlines are psi equal to constant lines. So you can easily do that by noting that x square plus y square plus my by psi, that is equal to 0, right. So you can write this as x square plus y square plus 2 m by 2 psi y plus right. So x square plus y plus m by 2 psi whole square. So it represents a family of circles, x minus a whole square plus y minus b whole square equal to r square, that form. So it represents a family of circles. The values of course depend on m and psi. So let us try to make a sketch without going into the values. So what is the center of this circle? 0 minus m by 2 psi and the radius m by 2 psi. So let us try to make a sketch. Assume m as positive and psi as positive. So this is x axis, this is y axis, 0 comma minus m by 2 psi and the radius m by 2 psi, right. So you have whatever is this distance, that is same as the radial distance. Even if you have a smaller radius, it is like this. Similarly, you may also, depending on the value of m and all this, you may also have it, a part of it at the top, right. So you may also have exactly the same way. So as if you have a source which is located very close to the origin and you have a sink located very close to the origin on the other side, and there is a flow from the source to the sink. That is what is it, it is sort of qualitatively representing. Now phi equal to constant lines, they will just be similar and orthogonal, that you can easily calculate by looking into that phi equal to m by r cos theta, again multiply both numerator and denominator by r. So it will be mx by x square plus y square, and that will represent sort of family of these types of lines. Okay. And these sets of lines are orthogonal to each other, and you can see that just if you look into plain mathematics, it is a very interesting way of generating orthogonal lines. This is just a way of thinking a bit differently from just the fluid mechanics perspective, but for us the fluid mechanics perspective is the important concern that we are talking about. Now we will consider another example. Uniform flow along x plus a doublet. Okay. So it is a superposition of uniform flow along x axis plus a doublet say of strength m. So what will be the resultant complex potential? First, due to uniform flow along x, that is u infinity into z plus m by z, right. So this is as good as u infinity into r e to the power I theta plus m by r e to the power minus I theta, right. So u infinity into r cos theta plus I sin theta plus m by r cos theta minus I sin theta. Okay. So u infinity r plus m by r cos theta plus u infinity r minus m by r I sin theta. So this is, we should remember that phi plus I psi, okay. Now let us say that we want to generate a body of a particular shape over which the flow is flowing by using this. We are going just one step forward. When you want to generate a body of a particular shape, we always have to keep in mind that the contour of the body is a streamline, because there cannot be any flow across it, right. So if you want to generate a contour of a body, it should represent a psi equal to constant. By convention that constant is taken as 0, that is the reference. So if you want to generate the shape of a body, the shape of the body should come out from the condition of psi equal to a reference which is 0. So the psi which is here, you can see that if you now generate the contour of a body, this should be 0. You can see that this psi solely depends on the radius r, right. So you can fix up a radius such that on that radius the psi is 0, and what is that geometry which is of a fixed radius? That is a circle, right. So let us say that you have at small r equal to capital R psi equal to 0. You can see that from this superposition that this, in this example, it is solely a function of the radius, not a function of theta, okay. So that means in that case you have u infinity into r is equal to m by r, that means m is equal to u infinity into capital R square. What is the implication? Implication is very interesting. If you choose the strength of your doublet as u infinity into some radius square, then you represent a particular flow. What is the flow? The flow in the plane is like past a circular body, that means in a 3-dimensional sense it is flow past a circular cylinder. So see, starting from very simple mathematics, we have generated the flow past a circular cylinder by combining a uniform flow with a doublet. So this represents flow past a circular cylinder of radius r. Okay. So what is the key? The key is you have chosen your strength of the doublet in a particular way, that is equal to mu infinity into r square. What is the velocity field? So let us calculate the velocity field. The velocity field will be calculated by differentiating f with respect to z. So df dz is u infinity minus m by z square, right. So this is u infinity minus m by r square into e to the power minus 2 I theta, just writing z as r e to the power I theta. M is u infinity into capital R square, that we will just keep in mind. Now we know that this we may write as Vr minus I v theta into e to the power of minus I theta. So what we do? We write this as u infinity into e to the power I theta, then minus m by r square e to the power minus I theta, the whole thing multiplied with e to the power minus I theta. So here it is multiplying by e to the power I theta into e to the power minus I theta to get just the same form of this one. So it is u infinity into cos theta plus I sin theta minus m by r square cos theta minus I sin theta into e to the power minus I theta. So u infinity minus m is u infinity capital R square by small r square cos theta minus I u infinity sin theta minus u infinity sin theta or minus u infinity minus m by r square sin theta, where m is u infinity into capital R square. Okay. So it is just like this has become Vr and this has become V theta, right. So when you consider flow past a circular cylinder, so you have a circular cylinder say of a particular radius capital R. We are interested to know that what is the velocity at the surface of the cylinder. Remember, this is not a viscous flow analysis, this is a potential flow analysis, therefore no slip boundary condition will not be satisfied. Okay. So what is Vr at small r equal to capital R? This has nothing to do with the no slip. This should be 0 at small r equal to capital R, no penetration boundary condition. So there is a circular cylinder on which fluid is flowing, so fluid should not penetrate the circular cylinder. So you can clearly see that at small r equal to capital R, Vr is 0. So this is no penetration, so no penetration is satisfied. What about V theta at small r equal to capital R? That is minus 2 u infinity sin theta, right. So you can see that there is a tangential component of velocity of fluid on the circular cylinder surface. This is a so called a slip type of velocity, and that is there because the potential flow does not have a consideration of no slip boundary condition. Now how do you find out the pressure distribution? See, we have found out the velocity field. So what is the situation? You have a uniform flow coming with a velocity u infinity. Now the fluid is flowing past a circular cylinder and we are interested to find out what is the pressure distribution and the velocity field. So to find out the pressure at some point, let us say we are interested to find out the pressure at this point P, which is given by the location say some r comma theta. Since it is like the theta is even 180 degree minus theta, if it is replaced it is the same. So it does not matter whether you choose theta in the proper polar coordinate sense or you choose theta from the left hand side sense, all the same. So see, because it is an irrotational flow and all other conditions are for the Bernoulli's equation, that is incompressibility, all those things are there. So you may use the Bernoulli's equation between any 2 points. So you may use it from a point at infinity to a point which is marked on the cylinder. So you have P infinity plus half rho u infinity square is equal to P square P plus half rho V square at this point. V square is VR square plus V theta square at small r equal to capital R, right. VR is equal to 0 and V theta is minus 2 infinity sin theta. So you can get a pressure distribution P minus P infinity in a non-dimensional form by half rho u infinity square is equal to 1 minus 4 sin square theta, because 2 sin theta squared will be 4 sin square theta, right. So this is known as coefficient of pressure, the non-dimensional pressure distribution Cp. So that means, see, we have got a pressure distribution and we may use it even for a boundary layer theory till there is boundary layer separation, because whatever is the pressure imposed by the free stream from outside the boundary layer, which is like a potential flow, same pressure is acting within the boundary layer. But of course this is the pressure at a point on the cylinder, and this pressure, the what you calculate even in the presence of a boundary layer, will not be too much different from this one till you come closer and closer to the apex point and you encounter adverse pressure gradients. So till the pressure gradient is very favorable, the actual pressure distribution and this pressure distribution will almost remain the same. We stop here in this lecture and we will continue again in the next lecture. Thank you.